I will begin with a word of prayer. Dear Heavenly Father, we just thank you again for this opportunity we have to meet together and study your creation. And pray that you'd be with us today. Help us to just again, Lord, to glorify you, Lord, in what we do. In my prayer, Lord Jesus. Amen. All right, so I was asked to work an example that is kind of sort of like problem such and so forth in the homework. So here's an example. This one's not quite the same as the ones I've done already, but the principle of calculation is the same. It's just there's like an extra sort of algebraic wrinkle in it. So here's the problem. Suppose you have x, y, z, xy is equal to zw, all right? And you also know that x squared plus y squared plus z squared plus w squared is equal to 1, right? So what's the deal with this sort of example? Like how to think about it? So what we're talking about is like some sort of four-dimensional space with coordinates x, y, z, and w. In this four-dimensional space, we're studying the solution set to two equations, right? So just generically speaking, if those equations are not the same equation, are those the same equation? Pretty obviously no, right? So they're genuinely different equations. So if you start with 4 degrees of freedom, you impose two independent equations, you ought to be left with two free parameters. So the set of x, y, z, w, which satisfies these two equations, is some sort of like surface in 4 dimensions. And so a surface in 4 dimensions, we can take 2 of the variables as independent, and the other 2 could be written in terms of those 2 independent variables. So that means we could write z as a dependent variable in terms of x and y, and w as a dependent variable in terms of x and y. Or, possibly, we could like pick y and z as dependent variables on x and w. So in this context, you'll have 2 dependent variables and 2 independent variables, which is different than what we did last time. Like last time we had 1 dependent variable and 2 independent or something, you know, counting was a little bit different. So if you have something like this, what you do is you just take the total differential and go from there. So let me just tell you what we're going to try. We're going to view z and w as dependent on x and y, and I want to show you how to calculate the let's calculate you know, like partial z, partial x holding y fixed, and partial z, partial y holding x fixed, you know, etc. All right. So how is that accomplished? Well, what I would do is I take the total differential of these equations, and that would give me, first equation give me what? It gives me y dx plus x dy equal to w dz plus z dw, right? And the second equation's 2x dx plus 2y dy plus 2z dz plus w dw, 2w dw equal to 0. I'm going to divide by 2. Because it's just nicer. All right? So I have, basically, you can think of it this way. I have 4 unknowns. My unknowns, in some sense, are dx, dy, dz, dw, and I have 2 equations, right? So to understand, you know, so these here, let me rewrite this again. So what I'm looking at is w dz plus z dw equal to y dx plus x dy. And let's see here, if I solve, this is going to give me a z dz plus w dw equal to, what is it, minus x dy, excuse me, minus x dx minus y dy. So what I need to do is I need to solve for dz equal to stuff like that. If I can do that, if I can solve these two equations and two unknowns, well, if I can solve these two equations for dz, if I can isolate dz somehow, then that will tell me what the partial derivatives are. Because the coefficients have that meaning. So how do you solve that for dz and dw? Well, the way I would do it is I would look at this as a little 2x2 matrix problem. This is y, z, z, w times the column vector dz, dw. And over here, and then I'll use something called Kramer's rule. Kramer's rule tells me that I can solve for dz by taking the determinant of what I do to solve for dz. I take the determinant of the coefficient matrix, which is wz, zw, and I leave this, since I'm solving for the first thing, the way Kramer's rule works, guys, since I'm solving for the first thing, I leave the second column alone. So that just stays put, zw, just like that. Ooh, let me make it bigger. zw, that stays put. And then what Kramer's rule says is if you're solving for the first thing, you take the coefficient matrix and you swap out the first column for the so-called inhomogeneous term, which is, in this case, is this mess over here. So I replace that with y dx plus x dy minus x dx minus y dy, like so. So this is what's known as Kramer's rule, which is something you might learn formally in, for example, Math 221 or maybe 321, but not always 321. It's more sort of an applied linear algebra thing. But anyway, this is standard technique. You guys, you electrical engineers, you'll use this to solve circuit equations a lot of times, right? Maybe your notation looks different. You use deltas or something, but it's the same animal. It's a way to solve linear equations. Yeah.
Sorry, what does that say in front of the brackets?
Determinant. Yeah. So this is actually w times y dx plus x dy minus z times minus x dx minus y dy. So it's that's that same determinant we've seen in the formula for the cross product, right? Like the determinant of a, b, c, d. Remember, it's ad minus bc. So this is, you know, a nice way to solve. And then downstairs I've got w squared minus z squared. So anyway, cleaning things up, we get dz is equal to, for my dx, what do I got? My dx, I've got wy plus x, plus zx, I guess, from the dx terms, and then divided by w squared minus z squared. All right, dx. Then plus parentheses my dy's. I got wx plus zy divided by w squared minus z squared dy. So thus partial z partial x holding y fixed is equal to wy plus zx over w squared minus z squared, and partial z partial y holding x fixed is wx plus zy over w squared minus z squared. So this is one way you can do this kind of problem. Now, in your homework problem, I didn't even give you, what did I do? I didn't even give you like the initial equations, right? In the homework problem, I just gave you like two differential equations, if you will. Two equations involving differentials. Which one am I talking about, guys? 53. So can you guys tell me what 53 is? Specifically what 53 looks like?
You are given dc plus dw equals x squared dx plus xy dy.
Uh-huh.
Next equation, dz minus dw equals e to the x dx plus the sign of quantity x plus w dy.
All right, so for this problem here, it was necessary for me to use Kramer's rule. See, when I'm facing these equations and I want to solve, my goal is to solve for dz, right? I needed some kind of technique because it's a little bit ugly to solve for dz, right? My example is a little bit harder than your homework problem. Do you need Kramer's rule to solve this for dz? How should you solve this for dz, guys? Add the equations. So that sophistication is not needed for your homework question, right? You add the equations, you solve for dz, the coefficients have the meaning of the partial derivatives. That's the point. Now, this example, because I actually gave you equations which govern the four variables, right? We could do this a different way. There's another way we could, let me show you the alternate route of calculation. So, and let's fix, we're going to calculate partial z, partial x, holding y fixed, all right? Find that, all right? So I just pick whichever equation. Let's pick the xy, xy plus, xy equal to zw, right? Differentiate with respect to x, holding y fixed. What's that give me? Partial derivative of the left-hand side is just what? Partial derivative, so we get partial. I'll write it down. So you guys at this point should all be shouting back at me, why? As in, why is the answer? What's that? Why? See, but it just doesn't ring true now. It's kind of like after I tell my children to apologize to my wife for whatever they did. If my wife overhears me telling them that, any apology they give after that point, it just rings hollow. I mean, you know, it's not going to work because I told them to do it, right? So it's not real. So, if we could travel back in time before I said to say that, we'd have something, right? But oh well. Anyways, my stupid jibber jabber aside, this gives us y equals to what? Over here, we've got what we're after, partial z, partial x. Wouldn't be lovely? That's all we're looking for. Times w plus z, but then here's the rub. Partial w, partial x, holding y fixed, right? And the thing is, if you're asked to find this, that comes with strings attached, right? This says that w is a dependent variable on x and y in this context, right? If x and y are independent, that means z and w are dependent, which means that w has to be understood as a function of x and y. And so, you know, great, this is what I'm after, right? But this is annoying. How to get rid of it? We also know that x squared plus y squared plus z squared plus w squared is 1, right? So partial differentiate that with respect to x holding y fixed. What's that give you? 2x plus 2z partial x holding y fixed, right? Plus 2w partial x holding y fixed equal to 0. And now all we have to do is take star and star star and solve for what I want, right? So this is star. Here's your star star. To solve, we need to solve that for what? for partial z, partial x. That's my goal. So I don't know, the way I do that would be maybe take the second one and solve for partial w, partial x, holding y fixed. What's that give us? Minus 2x minus 2z, partial z, partial x, holding y fixed, divided by 2w. Right? Algebra. And then take that, right? Take this monstrosity and plug it in right there. Then your first equation becomes an equation just involving partial z, partial x, right? Then you can solve for partial z, partial x. That's kind of how you have to do these. I mean, if you're getting paid for these, obviously you should demand more payment for services rendered if they ask you to do these ones, right? These are harder than the ones we did yesterday because they've got this extra wrinkle in them, algebra. Yeah? 2 equations and 2 unknowns, but still, yeah, a pain. Other questions you guys have about the homework? 51? Sure. That would be helpful. I should have printed this out if I had half a brain. Oh, this one. Well, what's your question about 51? The whole thing? The whole thing. All right. So suppose we had x plus 2y plus, z equal to 1, and we had x squared plus y squared equals to 4, right? This could be my S1. This could be my S2. I could ask you to parameterize the curve of intersection of these two, right? So I can draw a picture for this one. S1's a plane, right? It has normal. What's the normal? 1, 2, 1, right? And then what's the other thing?
That's a cylinder.
Right. It's a cylinder with radius 2, just like your homework question has a cylinder with radius root 2, I think.
Yeah.
Right. So the curve of intersection is that it's not a circle. Well, it's not a circle, right? It's something else. It would be a circle if it happened at the same value of z over the whole thing, but it doesn't, right? This plane is not horizontal. It's got some kind of tilting to it, so it doesn't slice the cylinder like transversely. It kind of like it slants. So it's some kind of like oval or something, right? This intersection. So how would you parameterize that thing? So there's C. By the way, so your homework question, the wording is not quite right. I mean, what I want you to find is a parameterization for each curve of intersection. There's actually 2 in that problem. There's one at z equals to the square root of 2, and there's another one at z equals to the square root of minus 2. Excuse me, minus the square root of 2. Square root of minus 2 is not a real number, despite the claim of a certain student recently. I'm in a test I graded, but anyway, that was a funny solution. What's that? Not you guys. Okay. Anyway, so how do I parameterize that?
First, I want to set those two equal to each other, so you like solve them. Well,
Here's what I would do. I would attack the weird one. The weird one's the cylinder. So if I want to make something go on the cylinder, what I would do is I would say, for this one, I would say x is equal to 2 cosine t. I would say y is equal to 2 sine t, right? And if I do that, at least I've solved the cylinder equation, right? Now, if this curve is also on the equation for the plane, then I need to put those into, 2 cosine t plus 4 sine t plus whatever my parameterization for z is. I don't know what this is, but it's got to be such that this sums up to 1, right? Oops, we just found z. So apparently z is equal to 1 minus 2 cosine t minus 4 sine t. There you go. So the parameterization of that curve of intersection is 2 cosine t, 2 sine t, 1 minus 2 cosine t minus 4 sine t. Does that make sense? And we can pick, let's pick a particular point to pick at. What's r of 0? Two, 0, minus 1, right? 2, 0, minus 1. So that's something like, I guess that would be this point here probably. If I use my usual, this is the z direction. So, well, anyway. Maybe it's that point. All right, it's where it's in the y equals 0 plane. X is 2 there, z is minus 1. So it could be in my picture that point, in principle, right? What's the tangent vector? What's r prime of 0? See, I asked you to describe the direction of the tangent as it relates to the direction of the normals to the two surfaces, right? So, I forget my wording exactly in that question, but to describe the direction of a curve, we should study the direction of its tangent vector, right? So, what is dr dt here? Well, it is what it is. What happens when you plug in 0? Well, you get 0 for the x component of the velocity. You get 2 for the second component. And this differentiates to, the thing that matters is the minus 4 cosine t, which gives me minus 4. The other thing goes to 0. So, there you go. The tangent vector would be 0, 2 minus 4. So I don't know how to, it's something like that, let's say, for the sake of discussion. Minus 3?
Oh, yeah.
So there's my velocity vector, right? What did we learn about, if we have a vector, right, we have a level function, right? And we take a path, right, which satisfies that level surface equation. We differentiate this, what do we get? We get the gradient of f at r of t, right? Dotted with dr dt equals to 0, right? So the velocity is perpendicular to the gradient of f, right? So that velocity vector should be perpendicular to what gradient vectors in this example? What's the normal to the plane? 1, 2, 1, 2, 1, right? So we should have v is perpendicular to 1, 2, 1. And what else should we have? It should also be perpendicular to what else? The gradient of the cylinder function, right? Which would look like what here? It points the outward normal direction to the cylinder, right? So that would be the gradient of, x squared plus y squared at the point what? 2, 0, minus 1, right? So what is that red vector I just drew? So the gradient of x squared plus y squared is just what here? 2x, 2y, 0, right? So this would give me 4, 4, 0, 0. So check it out. Is 4, 0, 0 perpendicular to the velocity? 0, 2 minus 4? Yep. Is it perpendicular to the normal to the plane? Well, 4, 0, 0 shouldn't be perpendicular to the normal plane. There's no reason for that. But is the velocity perpendicular to 1, 2, 1? 2 times 2 is 4 minus 4. Yep, dot product of the velocity and the normal to the plane is also 0. So can you describe for me geometrically then how is the velocity related then to the normals to the planes and the cylinder which form this curve of intersection? I mean, it's a vector which is perpendicular to both normals. So what is it? What direction does that have to be? How do we construct a vector which is perpendicular to a given pair of vectors? Cross product, right. Yeah. And that comment really has nothing to do with that this is a plane and this is a cylinder. You could just as well take two arbitrary weirdo surfaces, look at their curve of intersection, right? The curve of intersection, the tangent to that curve, right? It should be formed by the intersection of the tangent planes of the two surfaces at that point. And the line of intersection to two tangent planes is a line which is tangent to both planes, right? Which means it's perpendicular to both, which means it must be in the direction of the cross product of the normals to the planes. So the direction vector of a curve of intersection has to be given by the cross product of the normals of the surfaces intersected. Yeah. In fact, one of the ways I motivate the cross product formula in the notes, if you read them, is I show that you can derive the formula for the cross product by just looking at the line of intersection of two planes. And I do the algebra, work out the formula for the cross product as a consequence of that idea. Yeah. But anyway, other questions? Yep.
48? Yeah, 48.
48. What is 48 about?
Labeling a set solution of y squared equals x minus z squared is m, and it breaks down to two parts. Do you want to borrow my sheet?
Yeah, that'd be helpful. Thanks.
Yep.
So I give you y squared equals to x minus z squared as m, right? So the solution set of that is m, right? So I say A, write m as level surface for some f, right, of x, y, z. And then what was the other one? B, parameterize m using, I tell you x equals to, I told you the parametric equations for x? Well, come on. Well, I'm being too nice. Y equals to t cosine beta. So I told you everything except for z, right? Find the parameterization of z and then calculate the normal explicitly in terms of the given parameters. Find z equals to z of t or beta, possibly t and beta, and calculate the normal. All right. Thanks, Josiah. All right. I mean, it's really hard for me to write anything about part A without just solving it. What is a level surface? Similar question. How about that? X squared plus y squared equals to xyz. M, solution set. All right. So I could also write m as equal to, f inverse of 0, which is just another notation for x, y, z, such that f of x, y, z equals to 0, right? That's the level 0 surface for the level function f. So what's my f for my very similar but made up example? X squared. Yeah, just let f of x, y, z equal to x squared plus y squared minus x, y, z. Some of you are like, no, f of x, y, z was supposed to be 2 times x, y, z minus 2x squared minus 2y squared, right? That was what it was. Plus 7 equals to 7. That's what you should have done. I mean, my point to you is the level function is not unique, but unless you're a weirdo, you're almost all going to agree on the answer. You're going to agree on one of 2 answers, right? This or xyz minus x squared minus y squared, right? I mean, those are kind of the 2 natural choices here, given that statement. So that's it. I mean, that's write M as a level surface. So you say f of x, y, z is that, and that equal to 0 is the solution set to that is M. That's it. This is not the part you're confused about. No? No? I mean, it could be that you just don't understand what I'm asking, right? So I hope that, does that clarify? There's not much to do per day. Really, you just have to tell me what F you should choose. Actually, I mean, I'm saying you can make it be the level 0 surface, right? But you can make it be level 10. You just add 10 to your level function that worked for 0. I mean, there's, anyway, so I'm not going to say any more about A. You guys need to figure out A. Part B, to figure out what z is, right, I got y squared, right over here. I've got y squared equals to x minus z squared, right? And I already said use x equals to t squared, right? And I said y is equal to t cosine beta. Hopefully that's a help, not a hurt. I mean, it's a hint, it's a helpy hint, not a hurty hint. I don't know. We'll find out soon. What's that? I think it's good. It's good? Okay. It worked for you? All right. There's hope. So if we plug that in, that gives us t squared cosine squared beta equal to t squared minus z squared. So what should I probably make z then? Let's isolate z. Z squared is what? T squared minus t squared cosine squared beta, right? Also known as t squared times 1 minus cosine squared beta. Also known as t squared times sine squared beta. So it seems to me that it's kind of funny. Well, I mean, we got choices, right? We can either make z. I mean, there's 2 kind of choices to go with here. Does it make a difference? Z equals to, we could do z equals to t sine beta, right? That would work. Or we can make z equal to minus t sine beta. That would work, right? Hey, I'm solving your homework problem. What? Hey. Jerks. I've been trapped. Hey, I didn't tell you which one you got to choose. It doesn't matter. The other problem with the cylinder intersecting the sphere, it matters. The algebra leads you to plus or minus root 2. And those distinct possibilities give different curves. There's an intersection curve at the top and the bottom of where the cylinder comes into and out of the sphere in that homework problem, right? So there's really 2 curves, despite my wording that makes you think there's a singular curve of intersection. You should really find a parameterization for each curve separately. They're very, very similar. They just differ by a sign in the z component. But so what do you guys think? I don't think it matters. I think we can make z equal to t sine beta, and then what would the parameterization be then? We said x is t squared, right? Y was what? T cosine beta. And then t sine beta. There you go. That's a parameterization for M. Now, how do you calculate the normal vector field once you have the parameterization?
Partial R, partial T, cross product, partial R, partial T.
Right. So if we're looking for the normal, taking t and beta as the parameters in that order, then by definition, the normal vector field induced from the parameterization is partial R, partial T, cross product with partial R, partial beta. So you got some calculation to do there, but yeah. Now, if you pick a point that you can compare the level surface and the parameterization, what would this relate to? This would be interchangeable with what in level surface? They don't have to be equal, but they should be up to like a scalar multiple related to one another, right? What's the? Oh. Now, if I'm not careful, I'm going to write the answer to part A. If I did know f, I could calculate the gradient of f, and that should also be in the normal direction, right? But the gradient of f will be in terms of x, y, z, versus the normal vector field born of this calculation will be in terms of the parameterization variables, the t and the beta, right? What does this thing look like anyway, by the way, guys? This is just what, x equals 2? Y squared plus z squared, right? So what you're looking at is basically a paraboloid that goes out the x-axis like that. And so basically beta is swinging around. I mean, you give me a particular value for t, that gives us a circle, right? That would be x equals to the square root of t. Oh, excuse me, I'm an idiot. X equals to t squared, maybe? Okay, so like that's the x equals t squared circle. And then on that circle, your choice of beta will swing you around and pick a point. So that's how the parameterization is working. If you want to like look at it, you know, beta, what do we got? Y equals t cosine beta. So that means that beta equal to 0 gives, okay, so yeah. So this would be like, there's this right there would be beta equal to 0. Up here is like beta equal to pi over 2, right? And the back side of the circle would be beta equal to pi. It's swinging like that, I think. Yeah, yeah. So if I'm to draw, the circle's parameterized like that if we take beta as the parameter of the circle. Like that. But anyway. Any questions? Yeah.
47, where does dt come from? Like, I don't see a t
For 40.
I thought she's talking about 47B.
47, because it's dx dt equals this, where t comes
So suppose Pakun, a ninja dog, by the way. Pakun, it's one of Kakashi's ninja dogs. So, aren't you guys educated?
I guess we'll find out next
So here.
week.
So suppose this ninja dog Pakun speeds towards the base of a valley with a given shape. I give you the shape z equals to 5x squared plus xy plus 3y squared, where x, y, z are in meters, right? So assuming Pakun stays on the surface of the valley, if dx dt is 3, dy dt is 4, what's Pakun's speed? Now, for this question to make sense, you should assume I'm still asking at the same point as part A. Otherwise, it doesn't make sense because the way dx dt, dy dt, and dz dt are going to be related depends on where you are in x, y, z. So it's like a related rates problem.
Okay.
But, so where's the t coming from? We're thinking about the, you know, generically speaking, if you've got some kind of surface, right, and then you've got something constrained to the surface, right, you can think about that point, x, y, z, and that being at time t, you know?
Oh, yeah.
So it's a path on a surface, so that's where the t is coming from. And the fact that it's on the surface means that that x, y, and z are not just free to take on any values they want. If it's stuck on the surface, that means dx dt, dy dt, and dz dt are, they're interlinked according to the equation of the surface. I mean, if the equation of the surface was x squared plus 2y squared plus 3z squared equal to 1, then we would be forced to have the following relation between dx dt and dy dt and dz dt. Like 2x dx dt plus 4y dy dt plus 6z dz dt would have to be 0, right? I mean, if this equation, if you're stuck on that ellipsoid, then your x, y, and z coordinate velocities, they're not free to just vary over anything. If you pick two of them and you pick a point on the surface, you have fixed the third one, because that's a differential consequence of it being on the ellipsoid, is that the velocities x, y, z are related in that way. Now, the speed, what's the speed? Speed is not dx dt, it's not dy dt, it's not dz dt. So to solve part B, number one, you got to find what is dz dt. Great. Again, assume that you're in the same point as part A. Fine. You'll find dz dt if you understand that. But after that, I have not asked you for dz dt. I have asked you for the speed. How do we get the speed from dx dt, dy dt, dz dt? Do you guys remember?
We square them as an square that one.
Right. So it's x dot squared plus y dot squared plus z dot squared, because I'm tired of writing dx dt, dy dt. But yes, dx dt squared plus dy dt squared plus dz dt squared, square root of all of that, that's the speed. That's what I actually asked you for.
That's for part
Ah.
I was like, you don't have a variable t here.
Oh, yes, yes. It's our old nemesis time. If you look at this question, really, I could have asked this to a Calculus 1 class, right? It would have been a related rates problem. I mean, I do ask this kind of question to a Calculus 1 class, but then you really can't ask them for speed, because they don't know that speed is the square root of dx dt squared plus dy dt squared, unless you tell it to them, right? They may or may not know that, so I'm not supposed to ask them that. But in fact, if you go back and look at your Calculus 1, you'll find there's partial derivatives all over the place. We're always partial differentiating from the very start, because we have problems with A and B, just this arbitrary A and B. We're supposed to assume that they don't depend on x and y, right? So we're differentiating with respect to x and y, holding A and B fixed. I mean, that's a partial differentiation. There's partial derivatives everywhere. You just got to look for them.
Speaking of partial derivatives, I don't.
Nice segue, Josh. Here we go on. Quality.
I don't fully understand some of the notation and just how to do it once for a problem.
Problem 52. All right.
Like, maybe if you can give an example problem.
So problem 52 is very much like what I did at the start of class. It's got x, a y, a z, and a w. And you have two equations. So it's really just like the first example. You have two equations. They're both relating the rates of change of x, y, z, and w. Well, there is no w in the second equation, right? So it's a little bit nicer.
But with independent and dependent variables, so if it's in the bottom right, that means that there are independent variables and all the others are dependent.
Possibly. So let me do one like yours, but not the same, yeah? So it's something, that problem is more or less of the following form. It's something like w is equal to xy squared plus, sine of z cubed, something stupid like that. And you also know that x squared plus y squared equals to 7. I don't know. Then you're asked to calculate. Maybe that's wrong. Maybe Yeah. Well, let me say x squared plus z squared. Still wrong. You look at your problem again. Okay, x, y, z. Okay, so I need all three. Over here, we've got, I don't know, x plus y squared plus z to the fourth equal to 2, whatever, right? And so you're asked you're asked to calculate partial w, partial x, right? Does it say holding y fixed? Okay. So that tells me that w is a function of x and y, if you'll allow me this abuse of notation, and that z, well, z is also being viewed as a dependent variable, right? In my made-up example here. So what? So what I would do is I would take the first equation, I would differentiate with respect to x, right? So I get partial w, partial x, holding y fixed. And that would be equal to what? Well, that would be equal to y squared plus 3z squared cosine of z cubed partial z partial x, holding y fixed.
Last part, why is the partial x holding y fixed there?
Because z is a function of x and y.
Okay.
I can't take x, y, and z as independent in this case, no.
So any variable that is dependent, you do that with that. Okay.
Yeah. But then you see, to figure out what is partial z partial x in terms of x and y, you go to the other equation. This tells us that for z cubed partial z partial x holding y fixed plus 1 is equal to 0. So that means that this is y squared plus 3z squared cosine of z. Did I say z cubed? Yeah, z cubed. Yeah, z cubed. And then solving that, I get what? I get minus 1 over 4z cubed, right? And there you go. This is nicer than the problem I just erased because I give you an equation which says w equals stuff. So it sets you up nicely for w partial x with respect to y is equal to some expression, right? And then your goal is then just to remove things like partial z partial x holding y fixed because you have another equation which allows you to trade that away, trade that for, you know, the much nicer minus 1 over 4z cubed. Does that make sense? So tomorrow, guys, I will try to talk more about partial differentiation with respect to other coordinate systems. I'd like to actually find the formula for the gradient in polar and cylindrical and spherical coordinates. I won't derive all of it, but I'll do enough so we can have those formulas. Pretty nice. And of course, you can ask me more questions about your homework if you got it. So, thanks, guys.